Excellent. Well, welcome everyone in person and online to our first colloquium of the spring semester. And I'm very excited to introduce to you someone that many, if not all of you know already, Elena Vazquez-Peña. And we'll give her a brief introduction. I won't there's much detail to share about all of your accomplishments. I'll just give a kind of brief summary so you can get started with your exciting talk today. Elena Vazquez is a computational designer, researcher, and educator. Her work focuses on smart materials for adaptive buildings, and her interdisciplinary research bridges material science and computational design. Her work has been supported by a number of institutions and has received a number of awards, including the Upjohn Research Initiative Grant and the Architectural Research Centers Consortium, which recently, I think in 2018, you won an ARCC award, and then recently she won the dissertation award. There's just one given a year for a compelling dissertation. So congratulations for that. Elena holds a PhD in architecture, design, computing, a Master of Science in Architecture, and a graduate certificate in additive manufacturing from Penn State. She obtained her professional degree in architecture from Universidad Nacional de Asunción, which I'm sure I mispronounced, but wanted to convey that. And she's currently, as many of you know, a research fellow in design and technology integration at the David Raven School of Architecture. So with that, please join me in welcoming Elena.
Thank you, Blaine, for introducing me and for inviting me to give this colloquium. And I'm excited to be giving the first presentation of the year. And so thank you also for joining me here and those of you online as well. And so today I want to talk about my work in the area of kinetic facade design and smart materials and how that relates to natural systems and how we can learn from those natural systems to incorporate principles into facade design. So buildings account worldwide for about 1/3 of total energy consumption, and according to the World Bank, and that number is expected to grow as cities grow and GDP capitals also go up around the world. In the US, actually, that number is about 40%, according to the DOE. So total energy consumption, the building industry is responsible for 40% of that, and also the related emissions. And so if we take a look at building components, one of the building components that has largest impact on environmental performance is actually building envelopes. They regulate the energy exchange between inside and outside. And so they really have the largest impact on energy efficiency. So if we look at research into facade design and building envelope design, we can find that around 40 to 60% of total energy consumption can be reduced by rethinking building envelope. And this is really a stunning number because that means that if we focus our efforts and from a research perspective into improving the building envelope design and engineering, we can really have a large impact in total energy consumption. And so while most building envelopes that we find nowadays are static, really, if we take a look at outdoor conditions, we can see that throughout the day, a lot of the outdoor conditions really change. So sky conditions, temperatures, they all fluctuate throughout the day, but our envelopes are not really designed to respond to that dynamic change that we have throughout the day. And so this is in part because architecture is not really typically associated with dynamic or movement or change. In fact, all our conventional means of representation and means of thinking about architecture really privilege static materials. And so these ideas of dynamic envelope or dynamic architecture is really only recently started to permeate architecture practice. But on the other hand, if we take a look at natural systems and specifically some plant movements, we can find that their movement and their kinetics allows them to achieve specific functionalities. So for instance, some plant movements allow them to release seeds or to really harvest energy and be very efficient systems overall. And so the premise of this work is really how can we learn from this really efficient natural systems and incorporate some of those concepts into architectural design and building envelope design in particular. And so one of the arguments is that if we take a look at also this energy efficiency of living organisms, we can also, that could be one approach to tackle challenges of our time, such as climate change. And so this idea of kinetic building envelopes is not really a new one. We can see some examples built around the world of kinetic building envelopes and also some research on kinetic building envelopes. So for instance, there was a case of a research that found a 20% energy reduction with a kinetic shading aluminum pen compared to like a baseline case where it was static and optimized as well. And also some other numbers of kinetic blinds versus static ones. The research has found around 60% of energy savings as well. And some of the challenges of traditional kinetic systems, such as blinds and shutters, are related to the mechanical components that require maintenance, and also they are restricted sometimes to planar facades. And so this is where this idea also that comes from looking at natural organisms of elastic kinetics comes. And I want to talk a little bit about how what are elastic kinetic systems and how we can use them for building envelope design. So some definitions is that, so elastic kinetics can be defined as systems that achieve their movement thanks to the deflection of their members, meaning their components are elastic and therefore allow for some movements rather than having movable traditional joints. They are also called compliant mechanisms, but I'm going to stick to elastic kinetics on this presentation. And one of the major advantages that elastic kinetic systems have over traditional mechanical kinetic systems is that we can have a reduction in part count. So if we think about traditional joints and movable parts, they typically need all sorts of different gears and components to be able to achieve a kinetic systems. But if we think about elastic kinetics, we can really think about having locally defined stiffness, like plants do, to be able to achieve large deflections and movement. And so I've been working recently on a review article of elastic kinetics and taking a look at research that we have on different elastic kinetic systems. And for me, the way I like to make my review articles are always like redrawing all the different examples that I find from different case studies. And this kind of visual thinking also allows you to kind of start seeing on some patterns in the literature and seeing some opportunities for improvement or areas to work on. So this is a initial group of case studies that I've identified of elastic kinetic systems. And I'm going to show some build examples of how these diagrams transform into actual buildings. But as you can see, the arrows show where the input force is, and you can see on the left-hand side the initial state, and on the right-hand side, the transformation that these systems undergo when they are applied some force or movement. And so one of the groups or patterns that I identified were this elastic systems that rely on beams that bend. And so you see in the examples that I'm highlighting there, mostly they have a linear component that bends, and it's attached to a secondary component that actually makes this movement possible. So one example of this is the work by this team at Freiburg, they did this the system that is called Flechtofin. So basically it has a central beam that bends, and that simple movement translates into movement of this blinds that open and close. And also some other groups that I started to find. So the same applies to surfaces. So we can think about surfaces that have defined stiffness and how we can use that input force to be able to transform the different components of this kinetic systems and really achieve a reduction in part count. So if you were to try to replicate the systems with like traditional kinetics, you would really have a lot of different joints and such that would really increase the part count and maintenance and costs and so on. And so a lot of these systems also are inspired in biomimetics. So looking at plant movements and seeing how they have these elastic systems really can transform into some kinetic facade mechanisms that are more efficient than traditional kinetic systems. And so this is finally another group that is the ones that rely on buckling. And I'm going to talk a lot more about snap through and elastic instability in the second part of the presentation. But basically the concept is that these are also elastic systems that rely on buckling of their parts to be able to achieve this motion. And so a lot of these units can be repeated and they form all these different kind of skin systems. One other aspect that I've been noticing while working on this review article is that there's not much. So the unit tends to be repeated as is, whereas I think there's a lot of opportunity for parametric variation and using the material and the different stiffness of the material to really achieve like a functionally gradient skin with these compliance systems. So that's kind of one also area of opportunity that I identified in just looking at these case studies of compliant mechanisms in the literature. And so the idea is that we can use these elastic kinetic systems in combination with smart materials to achieve this really adaptive architectural skins. And so smart materials are materials that can change their property in response to environmental conditions. So they can adjust their properties dynamically. So for instance, a material that when you apply electricity to it, it folds or changes its color, those are all smart materials. And so this is a graph from a review article that is probably needs a revision at this point. It was published in 2019. But what we did was we identified what are the most commonly used smart materials. So shape memory alloys is one of the most commonly used. And we also identified a trend in using more and more of these materials in creating this architectural dynamic facades. And so if we think about the building envelope, there are all sorts of different functionalities that building envelopes need to attend to. And the one that, so for instance, protection, a lot of different functions can be grouped into according to protect the inside of the building, and also exchange, like control of interior heat gain and so on. But when I started mapping the smart materials into what building function they could help with, I started seeing that this group of shape-changing smart materials can really be used for control of solar radiation and to develop kinetic building envelopes that regulate the amount of daylight that comes into the building and thereby protects the inside and outside according to specific needs in different locations. And so this brings me to the first project that I want to talk about, which is about hygroscopic skins. So if, again, mapping all different smart materials that we have here, we can have all sorts of materials that when are applied when you interfere with different of their properties, you get a different response. So for instance, electric field that causes a stress, that would be a piezoelectric, those would be piezoelectric materials. And so the ones that I'm going to talk about now are materials that when they are exposed to water and they change their chemical properties, they present a stress response that is translated into a change in their and a bending change of their form. And so this really relates to the passive hydraulics, what is called passive hydraulics. So some of you may be familiar with pine cones that can open and close according to levels of humidity. So is this system, this principle actually that we can harness this passive hydraulic actuation that some natural organisms have, that we can really leverage for our own purposes to think about what can architectural skins be like that responds to changes in the humidity levels in the environment. And so this is graphic that depicts my methodology. And so what I like to think about my work in the sense that I have this combined bottom-up and top-down approach. So in the bottom-up approach, it's really about exploring with the materials, taking a look at what are the different fabrication variables, what are things that I can control in the terms of prototyping, fabricating with different materials, and this combined with this top-down approach, which is thinking about the overall configuration of the systems and how that is informed again in feedback loops from the manufacturing, from the bottom-up approach. And so this combination, this back and forth between the prototype and thinking about the full scale is ultimately this process is with what leads to the systems that I develop with my work. And so there is some research on using 3D printing for creating responsive or adaptive materials. So this concept of 4D printing was, of course, introduced by Skylar Tibbetts. I don't know what, I think it was like around 10 years ago. And so from that point onwards, there has been a lot of research using additive manufacturing, 3D printing, for creating systems that change their shape in response to different stimuli. So for instance, in this project, I'm looking at how we can print something flat, and when it's exposed to humidity, it can change its shape into a predefined form. And so these strategies of like, how do you actually do that? There has been some research from the material science perspective and also from the design point of view of how can we achieve that. And this is a graphic showing some of these strategies. And so what I want you to take from this is that we typically have a built-in anisotropic condition in the systems. That means that we control the direction of printing. For instance, in this one that is here on top, if we print all in one direction and then the next layer we print all in the other direction, that creates an anisotropic condition in the material that when it's exposed to humidity, it will tend to bend. So the same thing can be achieved in numerous ways. That would be the most simple thing. You can also control the tool path density. So if you print one layer of your print is like with like a distance of 1, and then the next one is with a distance of 10, you're also creating this anisotropic condition between the layers. And also you can get, you can use other strategies such as like having a restricted border. So you see, again, creating this differential condition that makes the material bend whenever it's exposed to humidity. And so the way that we've studied this is to do design of experiments, which is basically a statistical method that is to make a series of experiments in which you change certain variables and you measure the effect that changing those variables have on the output. So in this case, we were looking at bend. So we wanted to know which variables affect which variables would get us. Yes.
The slides are not changing.
Oh, that's too bad. Okay, so what I'm gonna try stop sharing and then re-sharing my screen. Maybe that'll work. Okay, stop share screen.
Or not sure, we didn't get it fixed last time.
Did that work?
It's on a different slide, yeah.
Uh,
Can you advance the slides?
Yes. Is it changing
There we
now?
go.
Okay.
Yeah.
Perfect. Okay, so I was talking about how we were using design of experiments, which is a method to understand the effects some variables have on the observed response. So we were looking at how much they would bend, basically based on changing different factors. And from this type of experiments, you get more control into achieving a desired response. So we were trying to design a system that had different levels of bendings. So one of the things that we found out is that, for instance, like the number of layers between the layers printed in one direction and the other really is the one that affects more the bending response. So we can use that for designing a system that has this desired response in when exposed to humidity. And one of the things that we were looking at here is to achieve what I called geometric amplification. So using origami geometries to be able to generate a large global response with very little local responses. So that means that you have a material that bends just a little bit in response to humidity, but when you design a system using this kirigami geometries, you can use that to amplify this very little and very subtle bending or shape change into something that really changes the shape that could be used from an architectural point of view, like in a building scale. And so we did a lot of tests with using kirigami inspired geometries. I know that kirigami is about cutting, and here we were printing, so that's why I say inspired and not kirigami geometries. And so we really were happy with the results in the sense that we were achieving a lot of very complex and large global responses from using these kirigami geometries. And so we created a system that in which we were simulating the shapes in using physics simulator in 3D modeling software, and we were dividing that surfaces and creating toolpaths based on that surface that we were identifying with the simulations. And so here's another prototype. As you can see, we were achieving this goal of having like a large global response based on very small bending response of the pieces. And we also published a manuscript in which we describe these rules. So like, how do you need to print with this material to be able to generate the desired response? So this was meant to be a tool for designers. And so to explain the behavior of this material and how to really print and achieve a desired response with this additive manufacturing techniques of like controlling the toolpath of printing and so on, and the order of the layers. So here is one of the largest prototypes we end up doing. In the end, we had some issues with this material going back to its original state. So we were getting like a 40% recovery of shape. So meaning we would print them flat, we will actuate them with humidity changes, and then we will change again the level of humidity so they go back, and we were only achieving around like a 40% recovery of the shape. So that's why I started looking into other materials for creating building envelopes. But still, I firmly believe that this is like a chemistry problem. So maybe in the future, I find a good polymer scientist collaborator, and this project kind of moves forward. And so there are really lots of different areas to explore in this area of hydroscopic printed structures using 3D printing to make these active materials. So sometimes just by looking at the literature, you can find these opportunities. So for instance, there's not been really research on using shrinking as a driver. So instead of like swelling with humidity, using shrinking as a driver for creating a fast response and so on. Okay, and so also one of the issues that we have with this type of passive hydraulic actuations is that achieving higher dimensional shape changes and also considerable timescales is very challenging. That means that passive actuation is very slow, right? So this research on 3D printed systems that change with humidity, usually the change happens over hours. So like 4 hours or so for changing from one state to the other. And so we know that if we want a truly adaptive system, maybe we need to think about shorter timescales, so minutes for changes instead of hours. And so that's also one of the challenges with passive hydraulic actuation, which is what I've been showing in the previous slides. And so that brings me to the next project that I want to talk about, which is snapping facades, which also uses a principle that is inspired by plants to kind of get rid of that very long time scales that we have with passive hydraulic actuation. And so in plants, we can see this phenomena of like very fast movements that are really sped up by elastic instabilities. So this is something that traditionally would not be desirable for buildings, and because we associate elastic or instability with failure, right? Structural malfunctions and so on. But we see that plants use to their advantage elastic instabilities to be able to achieve fast movements and large movements to, for instance, release seeds, trap insects, right? And so we can use those principles for generating more efficient architectural systems. And so in going back to my graphic, in this project, we were using both magnetic smart materials and also materials that were actuated with small electric inputs. And so going back to this notion of instability, in this project, we're using bistable elements. So a type, again, within the wide range of different materials that can be have elastic instability. These bistable materials have two stable state, as their name says it, and you can see them in the most common example would be snap bracelets. So they have two states, they can transition between one and the other by a small input force, right? And so the idea is to use those materials as architectural skins. And so this was one of the earlier prototypes where I started fabricating these materials and using them to start thinking about how can we have a kinetic envelope using this. And so a lot of my work is also about thinking about what are the different design variables that I can work with when I see a material like that. So this is one graphic that I did thinking about again, from the top-down perspective, thinking about how this can look like on a large scale and what kind of different materials, shapes and forms we can have to achieve that, that full-scale prototypes. And so this is a small video of the fabrication process. So the way these bistable materials are fabricated is that you cut pre-impregnated carbon fiber laminates. And so you layer them again with anisotropic condition layers on with one fiber orientation and the next one with the opposite fiber orientation. And the curing process, they go into the oven under vacuum, and the curing process leads to them having these two bistable states. So here are the two basic bistable states that they have. The idea was to start thinking about how we can use these materials for creating building skins at a large scale. And how can we actuate them with smart materials for achieving remote automatic actuation for them. And so in this project, we were looking also at the different scales of these materials. So from the thickness and understanding the orientation of the fibers to be able to achieve that kind of anisotropic material configuration that leads to this specific behavior, to the intermediate scale, number 2 there, showing the shape and form of the prototypes, to number 1, right, the full scale, and thinking how this can look like in from a building scale point of view. So again, a very similar methodological approach, looking at materials and systems from this two-way approach, from a bottom-up approach, prototyping with a material and doing tests at that scale, to a top-down approach to thinking about the full scale and how that can look like, what kind of improvements we can make at that point, and what kind of data we can collect to make those improvements at that point. And so from a bottom-up approach, really it was about doing prototyping and testing. So taking a look at the fiber orientation and how that affects the different bistable behavior. I'm going to try playing that again. So you can see here that they have different angles. They are tilted in different angles according to what orientation the fibers have. And so gaining control of the materials, the fabrication process to achieve like specific angles was really important for us. And also understanding how we can have like more complex systems in which this one piece can be connected to another and have this entire thing triggered and go from one state to the other by changing them by hand or with smart actuation. And so we're also measuring the critical force. That means what kind of force you need to change them from one state to another and how that relates to the shape that they had. So using force gauge and getting some data of understanding, would this be possible to actuate with shape memory alloy that I'm going to talk. So those are all preliminary research questions that we had while doing these prototypes. And so in my work, I like to think about iterative process. So I like to get to the first prototype as quick as possible. And this is one of the first prototypes. And so we were looking at manual actuation. So how can this be actuated in the most simple way possible? So by hand, using a frame that rotates. So this is a case here that you can see. It's not really by hand, but it's the frame that rotates and creates a snap. So here also, you can see what is the difference between those two states that we're talking about. And we're also using image analysis technologies to measure what is the different area between the two different configurations that we were achieving with those. Where is my mouse? Okay. So after getting those first prototypes, we started looking at different materials that we can use for actuation. So these smart materials are magnetoactive elastomers. And in this project, we were working with a group of students from the mechanical engineering department, and they were looking at how can they actuate the bistable sheets using MAE materials. So these are materials that are actuated with magnetic fields. And so one of the takeaways was actually what kind of magnetic field you need for actuating those at building scale, and what is the best configuration that they have to be able to use in this manner. And other materials include shape memory alloys. Oh, wait. And so shape memory alloys are materials that remember their state. So when we were applying electricity, so as you know, when you apply electricity to metal, it heats up, right? And so temperature was what's driving the actuation of the springs. And I'm trying to find my mouse so I can play those videos. Let me see. No.
It is on this.
Oh, okay. Oh, there it is. Okay, maybe I can play it from here.
Yeah, you're getting closer.
Okay.
There was a little.
Okay, there it is.
Here.
Oh, yes. Okay, so here you can see the spring being heated up with electricity and how that triggers the actuation of the flaps. And here you can see another video, again, the actuation being triggered by applying electricity to the springs. And so this is basically the schema. We have a material that changes, has different states in the microstructure according to the temperature it has. And here we're talking about 55 degrees Celsius, but that can be also fine-tuned. So imagine if we can use this shape memory alloys for a screen in a place where when it reaches like, I don't know, 80 Fahrenheit, it changes, it contracts, and therefore it makes the bistable laminate snap. So that would be really appropriate for some temperatures. So that can really be really fine-tuned according to the specific locations. And so we start looking also at how different configurations of the string path that is causing the actuation affect the force needed. So we were trying to use less springs actuators because these materials are more expensive. And we were also trying to decrease the part counts. So as you can see here, we were using 2 different springs. This one is a normal spring, and this is a shape memory alloy. And what is happening there is that one material is, so this one is contracting, but over time, this one will be pulled back into its original position because of the secondary spring. This is called a biased spring, and it's used in a lot of shape memory alloy actuation. Okay, I'm gonna skip this one. So we are also doing some FEA modeling to understand how much force is required for snap through, and seeing if we can create a model that would represent that in the digital space, so we as designers can understand what kind of force is needed, and also we can design the different actuation systems based on that information. And from a top-down approach, we were looking at digital models for simulating a specific case study in which we place the screen in front of it and collecting data based according to the daylight performance of this case study to be able to understand when we compare to actual data that we collected to see if we can have a model that is calibrated and that is validated. So what we did is we placed one of those screens in a test room and took actual measurements with light sensors to be able to understand how the daylight performance changed with the opening and closing of the system, and how also we can validate our digital model and compare the simulation data with the experimental data in this case. And so this is a picture of where we placed the screen. And you can see there one of the details of the shape memory alloys actuation. And you can see also that thanks to this bistable sheets, we can start designing things at a building scale with the time scale also barrier of like having actuation in seconds achieved versus like hours long passive actuation, which was the other project that I showed before. Okay. So Blaine, can you help me find my cursor? I can't find it. Oh, got it. Thank you. And so here you see another video of the actuation of the screen. I think it was like 4 seconds each to actuate each one of the flaps, and we were actuating 2 at a time. So that gives you, so that was also part of the process, reducing the number of actuators, just making it more efficient. Here you can see more footage of the screen that we created, and some details in the back for the actuation purposes. So this was all actuated with shape memory alloys. And well, kind of the next step of this project is that we want to look at how we can also not only control daylight with this bistable kinetic systems, but also harvest energy. And so this is something that I've been working here at UNC Charlotte with Kyung-hee as my new collaborator. And we're looking at adding more functionalities into the kinetic system to be able to not only achieve better performance, environmental performance, but also achieve some energy harvesting for the building inside. Because as you know, having photovoltaic integration in facade is really a very promising aspect, because that means that you can also embed all sorts of functionalities into smart facade systems. And so we're looking at different ways in which this can be integrated. So where like the position of the bistable laminates, the actuators, the photovoltaics, and testing out different scenarios so we can see which one works best for our intent purposes. And so the goal of this project is to develop a prototype that uses bistable laminates to control daylight, but also at the same time can harvest energy using photovoltaics. And this is the last project that I will talk about. And this project is called Kinetic Bamboo. And the idea came from kind of inspired as well with this new wave of research into wood, and really how these researchers have been showing how wood can be really elastic and can be formed into very complex shapes. So the bottom top ones are also using similar strategies to achieve bending of wood, but these are typically static systems. So what I want to look at is to how we can make bamboo specifically into kinetic facade systems. That's the main idea. And so the difference would be that we would be using curve bending strategies, but not to only bend the material and leave it there, but to actually have an elastic material that can go back and forth from one position to the other. And so the advantage of that over passive actuation, which is what we have in the lower two images, would be that we can achieve actuation in seconds, again, as opposed to hours. And so really more fast response to the systems. And so bamboo really has like it's a fascinating material that has a lot of research done in terms of mechanical properties and so on. And one of the things that caught my attention about this material is really that I'm not familiar with any project that uses wood for kinetic systems. And looking at material properties charts, because it's important to look at, what material you're dealing with and what are the limitations that they have. This was a really interesting graphic that shows what materials can be used for bending active structures, so things that you bend and you leave it like that, and for elastic kinetic structures, so things that constantly change shape. And so this graphic shows how bamboo is one of the materials that has these properties has the necessary flexural strength and ratio with the Young modulus that allows it really to withstand fatigue, basically, which is a challenge with the systems. So the idea is to develop an initial prototype using the same strategies that I was talking before, but the main fabrication strategy would be to use curve bending techniques. So taking away material from wood to be able to make it more flexible. And so these are some initial prototypes. So as you can see, we're trying out different thickness, different separation of the scores, distance, and so on, to be able to understand which one of them leads to more or less bending, so we can then design with them. And so similar methods, so using image analysis technology to measure the deflection. So here's one of the prototypes, and I'm using image analysis to measure the deflection and understand, so by changing the length, I achieve more bending. By changing the separation, I achieve less bending, and so on. So don't really have any finished prototype yet, because this is in very initial stages, but hopefully I have more data to show in the near future. So I as a conclusion to this part is that I think that new engineered materials let us reimagine our buildings as dynamic, responsive, and more efficient, and how it's super important to collaborate with different disciplines to understand and harness all the different capabilities of materials and be able to make our buildings more efficient that way. And finally, this is something that I just tried this week, and I thought it was fascinating, so I thought I will share with you to see what you all think. So you know how GPT has been out there for maybe a month now. And so I tried ChatGPT inside Grasshopper.
Oh,
And I asked it, can you generate a pattern that is inspired in wood texture? And the idea was like, can you give me a pattern that I can use for my curve bending, right, project? So I asked it to generate that pattern. And so this was the result. And so this really kind of, for me, this starts a conversation of how we can start using like, that's a pattern. The pattern is like, not really that much interesting, but for me, what is fascinating is to start thinking about how we can use AI as like research assistants to like get us to that first prototype even faster, right? And be able to enhance our research capabilities. Okay, that's last thing. Thank you.
Thanks. Are you suggesting that all of these prospective research assistants and rendered obsolete?
So I'm suggesting that they will enhance their capabilities by learning how to use AI technologies, and we will do even more better and good for the environment.
so creative.
Yeah.
Thank you for your presentation. I'm curious. It's really inspiring work, and I'm curious about, so I appreciate that you have the sort of bottom up and top down approaches that you're simultaneously thinking about. And I'm curious about in some of the systems, especially the second project, there's still a kind of modular approach where you're thinking of the unit, right? Almost like flowers that individually might change. Thinking from the top down perspective, or whatever you want to call it, kind of macro perspective of the system, having interdependencies, maybe getting to that functional gradient kind of goal that you talked about, such that forces or energies can propagate through the system as a kind of macro phenomenon. I'm just curious, and you might have to repeat that.
Yeah. Okay, I'm gonna repeat the question for. So the question was, so considering that the second project of my work was very modular, so have I thought about having a more analysis from the global side that informs the modular, so it's less modular and more gradient kind of thing, right?
Yeah, maybe so forces, like as the sun, moves around the building or whatever, forces propagate through, that there's interdependence.
Yeah, so interdependencies between the bottom-up and top-down approach in thinking about these systems. Yeah, that's a great question. I think that's one of the shortcomings that I saw in the review articles, in the making of the review articles, from looking at all those case studies that I showed in the beginning, that there is a lot of modular units being developed, and so I think that there's a lot of opportunity for this more gradient approach that you're talking about. And so that's definitely an area that I want to explore, even like how you can have, from a top-down perspective, have a gradient that then informs maybe the material, the way you fabricate the material. So it's not like a single unit, but rather you have like a gradient of units, maybe changing the thickness throughout the units to achieve this result. But yeah, I think that's a great idea. Yeah.
So you started with passive strategies, but materials things. So it's why you moved towards small electric currents to create more active systems. Are you wanting to, at any point, have an electricity-free system, or are you? Are you kind of like accepting that it needs electricity?
Yeah, that's a great question. So the question was passive versus active systems in this kinetic facade. So if I'm planning to go back to passive at some point, or stick with like the electricity driven systems. And so actually I had a meeting yesterday with a new collaborator, Simon Popinga from Freiburg University. He's a plant biologist, and we were talking about this actuation, right? Because I want to have, I'm looking into this bamboo elastic systems, and he was asking me, why don't we think about combining a passive actuation like a passive actuator, a very small one that triggers like a large response with this elastic bending system. So that's kind of the goal, right? I'm not sure yet how we're going to get there, but that's kind of the goal that I have in mind. Now, going back to passive actuation, but that can trigger a fast response due to this elastic instability of the bamboo systems. That's kind of the goal. Yes.
How has your like material science literacy evolved over the course of doing these exercises? Because I mean, I know there's for like really high altitude kind of research, you're collaborating with kind of folks in other disciplines, but I also expect that as somebody who's educated as an architect, that this kind of research is impacting your thinking about just like fundamental materiality.
Yeah, that's a great question. Thank you. So the question was like, how do I know about materials? So I took some undergrad courses on material science in Penn State, and it was a very humbling experience. Very different from architecture classes, like stadiums full of 400 students. And so and it was that, I think that gave me the basics, like just having a basic coursework on material science. Even like as an undergraduate level, it was like I learned, my learning curve was like very steep. But also just collaborating with folks from different areas forces you to gain literacy over the projects, because maybe just by like sharing papers that they like with ideas that they have, that's when you start learning the terminology, the shared language that you can have with them. And so that kind of pushes you to gain that knowledge to be able to work this way.
The discussion about passive versus active raises different thoughts. So one would be passive house as a design process or methodology. And there's a counter, or not necessarily counter, maybe it's a kind of counterpart effort that's a little bit more grassroots, which is active design or active house, which isn't as well known, but this idea that we can have dynamic components to help us save energy as opposed to design with ultra thick walls, insulated walls. So I'm just curious your take about a kind of directionality of design as a kind of climate response. Is your position that active design or that kind of dynamic design is required to mitigate or adapt to the climate change crisis? Or
yeah, I mean, it's funny that I mentioned passive house design, because they are typically like really enclosed spaces, right? That have lots of insulation and such. And so whenever I think about testing the systems, it's always like, okay, this is the enclosed box and we're putting the screen behind us. But I wish there was a way of starting thinking about gradients of like inside outside, like we're talking about in your colloquium. I'm more towards, like, me personally, I'm more interested in having that discussion of like gradients of inside outside. But I do know that from a science perspective, it's just much more easier to think about the enclosed box, right? So it's like a back and forth, right? Because for testing something, you want to have this enclosed thing, but actually for implementation, it might be like more interesting to think about inside outside as gradients, and not like as this barrier. Yes.
I think I'm in the energy requirements of sort of the active kinetic system we're talking about, and how anything that maybe produces solar cells that you're mentioning at a certain point is a way to sort of offset that energy requirement to make them more truly efficient, so they're not. I know it makes it more efficient, but to sort of offset.
Yeah. That's a great question. So when you finish asking that question, I realized I didn't put a graphic where I show the energy consumption calculation of the screen compared to energy consumption that is saved. So that's actually something that is one of my latest manuscripts published, is that calculation, right? Figuring out how much the screen consumes versus how much the screen saves. And we did find that we still have savings from the screen versus the consumption. But I think that offsetting even that energy consumption is a priority. And that's why we're looking at solar cells for harvesting energy. So yeah, thank you for that question.
Yeah, like maybe the expression, spend money to make money. Sometimes you have to use a little bit more to save a lot of energy. And in architecture, we tend to design in binaries, like you're saying, it's inside or out, or it's active or it's passive. And a lot of times when we're talking about passive strategies, it's like nostalgic return to the vernacular, which is I think dismissive of a lot of the innovations that we've done over the past, however many years. So what I appreciate most about what you're saying is like designing within this world of gradients, and that you're mixing passive and active. It's not one or the other, but it can be both and.
Yeah, for sure. Yeah, I think that there's a lot of opportunity of innovation in passive design, thinking about, how smart materials can be passive and still be part of like this discussion of, low energy housing solutions.
I like to call it passive plus, so it's like passive-ish.
What's
Yeah.
interesting is some of the passive material strategies, they move. Right? Some of the like hygroscopic materials or things might be called passive because we're not adding electricity to them, but they are dynamic.
Exactly. Yeah.
The terminology is different.
Yeah. Awesome. Thank you so much. Thank you, everyone.